Last time we started the consolidation test, and we said we will finish it off this time. I'll do, I guess, a quick review of what we talked about last time, and then at the end of the class, I'll talk about what needs to happen as far as the report for this lab and what you need to calculate for it. So this is a consolidation test. Basically, you have a sample inside of a ring. You have a porous stone on top, a porous stone on the bottom, and then you apply a load and you wait for water to leave the soil sample. And you take a couple of measurements using a dial gauge for the strain. And from that, you can calculate C sub C, C sub R, and C sub V, coefficient of consolidation, to calculate the time rate or how long it takes for consolidation to take place. We said that consolidation basically is water being squeezed out of the soil once an external load is applied. And here we're talking about clays, or we're talking about a combination of cohesive soils, saturated soils that do have water in them. I think we talked about the piston and spring analogy, and since you guys now reviewed the stress, you now all know what effective stress means, correct? I think that was the lecture in class, the last one. So maybe we should just mention quickly this spring and piston analogy so it gets kind of stuck in your head. Basically, what you have is you have a piston, and what did I do? Yeah, I think this looks good. So basically you have water here and you have water all around this this sample. So it's in like a water bath. And the reason why this analogy is useful because it explains the process of consolidation. So basically, initially we have a sigma naught, so initial stress. And if we take a look at three things, if we take a look at total stress with time, and we take a look at pore water pressures with time, and if we take a look at time and effective stress. And remember that effective stress is equal to the total stress minus pore water pressure. So initially, we have some pore pressure and some stress on the spring. Now here we have, oh no, okay. So here we have two valves, and these valves are closed. Then what we do is we'll add an additional stress to the sample, and these two valves on the right and on the left are closed. Now, once we do that, what's going to happen is you're going to have an additional pore water pressures generating. So you're going to have an increase in pore water pressure, right? Because the valves are closed and we are compressing it. So we're going to have an increase in the pore water pressure. And that will look like something like this. And it's going to be proportional to what we the stress that the extra stress that we applied. Now, what's going to happen to the effective stress here? It's going to stay. It's going to stay. It's going to stay the same. Now, once we open the valves, so once we open this valve, and think of this valve like clay, like it's a small, tiny valve, like clay's permeability, like water can squeeze out tiny bit by tiny bit, and we saw that from the permeability lab. And what's going to happen is this pore water pressure, or the extra pore water pressure after we open the valve, it's going to start to go down because we have opened the valve, and it's going to keep going down until it levels off to whatever initial pore water pressure we had. Now, for the effective stress, that is going to increase because the pore water pressures went down. And that's basically a consolidation process. So the soil is your spring, and you're observing what's going on in terms of effective stress and pore water pressures as consolidation is taking place. And basically the volume of water that is going to be leaving the sample is going to be the same volume that the sample will compress, or the change in the voids ratio for the sample. That's going to be equal. And that's consolidation. So is that clear?
Yeah.
So,
yeah.
okay. So if you understand this, then you understand consolidation, basically. So this is kind of reiterating what I said. The settlement is directly proportional to the decrease in volume of soil. So the decrease in volume of soil, or the decrease in voids, is equal to the volume of water that is leaving the sample. And this is a comparison that we mentioned last class between compaction and consolidation. They should not be confused. One takes process over a longer period of time. One is instantaneous. Consolidation applicable to saturated soil, and when we say saturated soil, meaning, remember we said like that the sample is composed of voids, and we have the solids. So basically this voids is only composed of water. We don't have any air. That's what we mean by saturated. Now, we talked about immediate consolidation. So first, the rearranging, elastic deformation of the soil, and then primary consolidation, which is what we are interested in. That's the maximum change in volume. And secondary consolidation, which happens after primary consolidation. It's adjustments of the soil fabrics. So again, we said we wanted to obtain the time rate of consolidation, so how long, and the amount. And we do that by, if you remember, we said we have a C sub C, which is a compression index, and we have a C sub R, which is a recompression index. So C sub C for compressibility of the soil, and C sub R, it's the rate of the compression for over consolidated soils. And I don't think I have, okay, I don't have a slide for that, but so when we say normally consolidated soils, so NC soils, what we mean by that is that a soil that has never experienced a vertical effective stress that is larger than the present vertical effective stress. So basically, that's you have to kind of understand or memorize this definition, it's simple. So a soil that has never a vertical effective stress that was greater than the present effective stress. So is this clear? So the soil never felt a stress on it that was higher than what it's feeling right now. So does that make sense? No response? Does that make sense? Hello? Are you guys writing it down?
Yes, it makes sense.
Everybody else? Yes. Oh, okay.
Yeah, it makes sense.
Okay. So that's normally consolidated soils. Now, over consolidated soils or OC soils, and again, I just want to mention this so when I refer to normally consolidated or over consolidated, you have some idea. But in your lecture, you'll go in depth with each one and 3 cases that are used to calculate settlement. But OC soils or over consolidated soils, they are soils that has experienced a vertical effective stress higher than the present. Vertical effective stress. So basically at some point, I may have touched on this last time. I said that if you imagine there was an ice age and ice has a weight, of course, and it was on the soil, then the ice melted. So whatever is right now on top of that piece of land that you want to build something on has experienced a vertical effective stress more than it's feeling right now. So it experienced larger vertical effective stress than what it has right now. And that's over consolidated soils. So is that also clear?
Yes.
Yes.
Okay, that's good. So now the coefficient of consolidation, we said that that CV, we can obtain it from the plot that we get from the consolidation test. And we can use that to find how long it will take for 60%, 70%, 90% of consolidation to take place. And we'll take a look at this. Now, we also said that we have a prefabricated wick drains. These are practical solutions to the consolidation problem. So you try to induce consolidation so that you can build up without having excessive settlement or without having differential settlement. And I think we also talked about what's the difference between both of them. Now, in this case, this is the consolidation meter that we have. So basically, you'll have a soil sample in here, and again, you have different load sequences that you're going to apply. You start maybe with half a ton, 1 ton, 2, 4. Then you might unload back to 1 or back to half, and then go up all the way to 32 tons per square foot. And with that, you have a dial gauge reading, and you are reading the decrease in volume or the increase in volume in the unloading phase. And we mentioned also how you can set up this test and how the ring is, and you have a load plate and you keep on changing the loads, and you have to be careful to kind of change the loads very quickly. There's one consolidation meter that is more kind of like a black box. Basically, there's the load is being applied, and then it can be unloaded with like kind of something that looks like there's a load cell, you know, in mechanics of material. When you broke concrete cylinders, you have that machine, I forgot what's called, that's pressing on the cylinders, breaking them. And it can do the same, or this loading sequence. Now the handouts, I gave a handout for the Taylor's method and for Casagrande's method, both of them, and we mentioned them both, but I'm gonna go over them because I didn't manage to get a good recording for the last class, so we're gonna use this one so you guys can share it between you. And this is a data sheet from a university that we received. So basically, these are the measurements that you will need at the beginning of the test. You have the mass of the ring, that, remember the ring that the soil was pressed into, the inside diameter, the height of the specimen, this will be used in your calculation, the area of the specimen, this is an easy calculation because you know the area and you know the height of the specimen, the mass of the specimen and the ring, and the initial water content, which we know how to find, which we take a can, we weigh the can, we take a soil sample, we put it in the can, we take the weight with the soil sample, put it in the oven, take it out of the oven, and take the weights, and we can calculate the water content given the specific gravity. And then after the test, you will also do this, and notice how you're looking at the change in the moisture content before the test and after the test. With that, what you need to or what you would be expected to calculate, you have the mass of solids in the specimen, and you have the mass of water in the specimen. You know, we know the water content initially, we know the mass, so we can calculate the mass of water in the specimen. After the test, we also have the sample, we got the moisture content after the test, or water content after the test, and then we can find the mass of the water. Now for the height of solids, this is also a simple, straightforward equation. Here we have the mass of solids, which we have the area of the sample, specific gravity, and unit weight of water. Oh no, sorry, density of water. So this is 1, and this is 1 gram per centimeter cubed. It's right here actually. Well, unit density of water. And then you can find the height of solids, because you need the height of solids in your end graph, which will be the voids ratio with the log pre-consolidation pressure. Now, the height of water before the test. So again, we have the mass of water initially, we have the area, we have the density of water, and we can calculate that. The height of water after the test. So we also have the mass of water after the test, we have the area, we have the density of water, and we can calculate the height of water. Now the change in height after the test. So remember, this is, you can see here, sum of delta H. So basically, these are the loading sequences that we're going to use. So we have a 1/8, 1/4, half, 1, up to 4. Then we do unloading, and then we load it all the way up to 32 tons per square foot. And for each of these loading sequences, you will have a graph, time, log scale, and you'll have a dial reading on the y-axis. And from this graph, you can use either, no, actually, if it's log time, you can only use Casa Grande to get the T50. And remember, we need the T50 because CV, coefficient of consolidation, is equal to T50 multiplied by what? What is it multiplied by? The drainage height, and that is divided by T, 50, right? Yes. So from this graph, you can get T50. And remember the drainage height we talked about. We have our soil sample here, and the drainage height is the longest path that the water needs to take before it can leave the soil sample. So if we have two-way drainage, basically here we have on top porous stone, on the bottom porous stone, then what's the furthest path that the soil can, or water has to take to leave the sample? It would be this. It can either go up or down. So the height of the drainage layer, it's for two-way drainage, it's going to be HDR. It's going to equal to the total height. This is the total height over 2. For one-way drainage, then basically, if the furthest part from it, if this is impervious or this is rock, impermeable, so the longest distance that the water needs to take is the whole height. So HDR for one-way drainage is equal to H. And we mentioned that we have, our case is two-way drainage, but when we calculate CV for each time step, for each load increment, it's gonna change. Why? Because this height of soil sample has undergone some deformation, and we need to deduct that from the height or add it if it has increased in volume by this strain or this change in volume. So you have to be mindful that you have to take this delta H into account when you calculate CV, because it's no longer the total H. We have a decrease in volume or increase in volume in unloading, and that has to be taken into account to calculate the CV value. Now, if we go back and quickly review the Casagrande's method, basically, first off, you select the time somewhere on this left side of the screen, where less than 60% of the total consolidation has taken place. And then you take a straight line up to the graph, and with that you can go to the y-axis with a straight line, and you'll call this D naught, for example. Then you will say that 4 times T1. So 4 times that. So 1, 2, 3, 4. So you will go over here, and you will take another straight line, and this, you'll call this D1. So or you call this D1, and let's call this maybe, no, D2. Now this difference, delta, what we'll do with that, we'll take it and we'll add it to D1, and we'll go up, let's say this much, the same exact amount as this delta, and we'll go right here, let's say Okay, and this is delta. And we'll call this D naught. Now we have a value for D naught, and the reason why we want D naught is because we want to calculate D50. And D50, this is just a weighted average. Now, the way you get the D100 is you go to this, you find the straight region from this primary consolidation part. So, and you take a straight line to it. From secondary consolidation, go with another straight line. And where these two intersect, you call this D100. And with that, you can find D50 by D naught plus D100. It's right here while I'm writing it. Divided by 2. Now you have D50. Now, if you want to calculate or you want to find D50, you go to where D50 is with a straight line. This is the final one. So this is the important one. This is what we need. And so it's somewhere, let's say right here. And you see where this intersects, this graph. And then you will go down to the x-axis, and this will be your D50. And again, we need that because we need to calculate C sub V, which is dr squared multiplied by multiplied by T divided by T50. Or in this case, 0.178, I think, right? 0.178, is it? Let's see. Yeah. So this is it. CV is 0.97 HDR squared over T50. So where were we? Here. So this is the equation that you will use. By T50. And now you can calculate CV. And you can use that to approximate the time rate or how long it will take to achieve whatever consolidation your project wants to achieve, or what is the settlement that you can tolerate in your specific project. And you see that there are the same exact graphs for each load sequence. So 2 for 2 for 4, and this is unloading. I think they unloaded up to what? To 1, to half, then they reloaded all the way up to 32. And with that, you can calculate C sub V. Now, is this clear for everyone? I think it is. I mean, we reviewed it twice.
Yes.
Okay. So that has to be done for every load sequence. And I'll tell you at the end of the lab what we need to do for our lab. We're not going to use this same exact load sequence. Now, another important plot that you get is here, the void ratio and pressure. And this you can get, so again, we know how to find time for 50%. This is all from Taylor's method. And then we have this delta H. We can calculate the change in height or the total cumulative change in height. So basically this line plus this guy is this number. And then same for each load sequence. And this is the total, the cumulative sum. H, so the height of the solids, and this is the drainage height. And remember, we said that the drainage height is going to be the total height divided by 2, because we have two-way drainage, minus whatever deformation we have. And from that, you can calculate C sub V. And that's the coefficient of consolidation. Now, the height of voids, we also do have that, because at the beginning, actually, yep. So here, you can calculate the void ratio before the test and the void ratio after the test, and you can find these numbers. So this is the HI, so this is the initial height. In this case, HI was 2.7. This is the height of the specimen. It was 2.7. Then minus the height of solids divided by the height of solids, and that's our void ratio before the test. And our void ratio after the test is the same. It's the same calculation, except we're going to use the final height of the sample after it deformed. So this is the HF. This is the cumulative sum of all the deformations, and that's the height of our sample. And with that, you can calculate the void ratio after the test, because you have the height of solids. That's not going to change, but what will change is the height of the sample. It will change. It will compress. And in here, we can do this calculation, because we have HI and we have the height of solids minus the total deformations, and then we can find the height of voids. With the height of voids, what we're going to do, the final step, is just it's the same exact calculation I just showed you, except here we have a height of voids that changed, and the height of solids stayed the same, and so the void ratio is going to be changing. And you just have to be careful during unloading. You don't minus, you add, or during unloading you subtract, you don't add, for delta H. Now, after you've plotted this void ratio right here on the y-axis, and the pressure here, again, log scale, you will have a consolidation curve that looks something like this. Now, this is a very important one, because I think, did I talk about this? I think it's here. So this is the pre-consolidation stress. Okay? So, or pre-consolidation pressure. You can use them interchangeably. So this is the maximum stress that the soil has felt in the past. And it's important to do that, because what do we want to do? And again, I'm just going to touch on this. The consolidation ratio over consolidation ratio, this is equal to this pre-consolidation stress divided by the effective overburden pressure that you have right now. And if this OCR is greater than 1, then you have an OC soil. If the OCR is less than 1, you have a normally consolidated soil. Right? Yeah. So with that, so you need those to kind of to find what degree of consolidation you have. So we need to find this pre-consolidation stress. And the way we can find this pre-consolidation stress is from from the plot we were just talking about, from this plot. So again, the quality of this curve will depend on the sample disturbance. So it's a very disturbed sample that they did the test on, and if they perform the test according to standards, then we will have a better quality curve. And what I mean by that here, it's important to find this maximum curvature, or where this line is going to go from being, if we draw this perfectly, something like, oh, perfectly. So we want to see where this maximum deflection or maximum curvature point is. And if we look at our curve, it is somewhere right here. And this is, again, also a graphical procedure that you will use to find the maximum pre-consolidation pressure. So you'll go with a straight line horizontally. Let me erase this. Just imagine this is right here. Then what you would do is, okay, you come from this area where you have, you're gonna draw a tangent to this curve, where that point is, just a tangent on the curve, where this point is. And I know I exaggerated the point. And then what you would do is, you have here a total angle. Let's say this is theta. You're gonna draw a bisector. So on each side, you're gonna have half of this. So theta over 2, and here you have theta over 2. And then with that, you come from this region of the curve and you draw a straight line. And where this straight line intersects with the bisector, you go straight down to the x-axis and find the pre-consolidation pressure. So is that clear?
Yes.
It's the kind of the same thing that we did in the C sub V, except it's easier here because you don't have to do this delta and add and come back. It's a straight horizontal line. You try to look at the curve and see where this maximum curvature is. You draw a horizontal line. You draw a tangent to that curve at that point where you drew the horizontal line. You bisect it where and then you go from the bottom end of the curve up to the bisector where that intersects. That's the pre-consolidation stress. And again, we try to do that because we want to see in which region we are in. So we want to know if we are normally consolidated, overly consolidated, case 1, and overly consolidated, case 2. There are 2 cases. And I'm sure you will look at them in the class. And this is the unloading part, and this is the CR recompression index. And you can use that depending on if you are normally consolidated or over consolidated. And I think, yeah, so here you have a CV value. Look, it's like a range. So it's not, it can be reported like this in geotech reports, but it also can be just a kind of an average value maybe for each layer or for all the layers together, depending on what you're trying to do. And I think that's it for